You know, there's a type of number that has, hands down, the absolute worst name in all of mathematics: imaginary numbers. Just the name itself feels like a joke, right? It suggests something that can't possibly be real or useful. And honestly, for centuries, that's pretty much what most mathematicians thought too. But that brings up the big question, the one that stumps so many of us in math class. If they aren't real, why in the world do we have to learn about them? What does it even mean for a number to be imaginary anyway? And listen, if you've ever felt that way, you are in very good company. I love how this Reddit user puts it. We can all picture positive numbers. We can picture fractions. Heck, we can even picture negative numbers if we think about debt. But the square root of -1, that doesn't really connect to anything we can touch or see. So what are we all missing? Okay, to figure this out, we need to frame the problem in the right way. The confusion around the imaginary unit, which we call I, the square root of -1, it isn't really about the number itself. The real problem is that we're all trying to understand it using just one dimension. We're stuck on that basic number line that goes left and right, from negative to positive. We're essentially trying to find a one-dimensional answer to what is actually a two-dimensional question. And that is the absolute key to the whole thing. To understand imaginary numbers, we have to give our numbers a second dimension. We need to stop thinking about a line and start thinking about a flat plane. Think about it this way. What happens when you take the number 1 and multiply it by -1? You land on -1, right? On the number line, that's just a 180-degree flip, a full half turn. So here's the puzzle. What operation, if you did it twice, would give you that same 180-degree flip? Well, a 90-degree turn. And that is what I really is. So let's just stop thinking of I as a number for a second. Let's think of it as an action, a command. It's an operator that simply means rotate 90 degrees counterclockwise. It's not a quantity, it's a transformation. Let's walk through it. Say you start at the number 1 on that horizontal axis. You multiply by I, and boom, you rotate 90 degrees up to the vertical axis, and now you're at I. Now do it again. Multiply by I one more time. Another 90-degree turn, and where do you land? At -1. Suddenly, that rule from math class, I squared equals -1, isn't some random thing to memorize. It makes perfect visual sense. It's just 2 quarter turns. Okay, so it's a pretty neat geometric trick. But what is it actually good for? Well, it turns out this imaginary idea is one of the most powerful shortcuts in all of engineering and physics. This engineering student on Reddit just nails it. They said, these numbers aren't here to make our lives harder. They exist to make incredibly complicated problems much, much easier. Just take the alternating current that powers everything in your house. It has 2 things that are constantly changing: its strength, or amplitude, and its timing, or phase. Now, if you try to describe that relationship using regular math, you're wading into some really messy calculus. But if you use complex numbers, numbers with a real part and imaginary part, engineers can just use the real axis for amplitude and the imaginary axis for phase. And just like that, all that nasty calculus turns into simple algebra. It is a jaw-droppingly useful tool. And this same idea just keeps on building. If complex numbers are the perfect way to describe rotation in 2 dimensions, what happens when we need to describe rotation in the 3-dimensional world we actually live in? Well, you guessed it. We need to expand our number system again. And here's the really wild part. To handle 3-dimensional rotation without running into some serious mathematical headaches, you have to jump from 2 dimensions all the way up to 4. And this realization led to one of the greatest aha moments in the history of math. So picture this: October 1843. An Irish mathematician, William Rowan Hamilton, is taking a walk with his wife. The problem of 3D rotation has been eating at him for years. And then, as he's walking along a bridge, the solution hits him like a bolt of lightning. He got so excited that he actually carved the basic formula into the stone of the bridge right then and there. That formula was for something called quaternions. So quaternions are a 4-dimensional number system. They have 1 real part, like complex numbers, but now they have 3 imaginary parts: I, J, and K. The easiest way to think about them is that each one represents a 90-degree rotation, but around a different axis in space: X, Y, and Z. They follow some special rules, but the core idea is exactly the same. 2 90-degree turns around any one axis gets you a flip to -1. And if you're thinking this is just some abstract math thing, think again. Quaternions are the invisible engine behind almost every 3D rotation you see. We're talking every single video game, every CGI movie, the navigation systems and robots and spaceships. They're even used to process the data from an MRI scan. They are everywhere. Which brings us right back to that name. If these numbers are so fundamental to how we describe actual reality, why on earth are we still calling them imaginary?
Well, the truth is actually a little bit petty. Back in the 17th century, the famous philosopher and mathematician René Descartes, he just thought the whole idea of taking a square root of a negative number was completely absurd. So he coined the term imaginary as an insult, to throw shade at the concept. And unfortunately for all of us, the name stuck.
But they are so far from unreal. What they really are is a profound discovery that numbers can have more than one dimension. They are the language of rotation, of waves, of anything that has a cycle. They're an absolutely essential tool for describing the physical world around us.
So I guess the big takeaway is this. Sometimes the most abstract, imaginary-sounding ideas are actually the keys that unlock a much deeper, more accurate picture of reality. Which really makes you wonder, doesn't it? What other concepts are we dismissing today that are going to turn out to be the essential tools of tomorrow?